Okay, so now that we have a clear understanding of what oxidation numbers are and why we use them, the next step is to learn how, when given any molecule or compound, how to assign oxidation numbers to the different atoms of the compound. So here's the rules that the textbook gives. This looks like a lot, but it's not as difficult as it seems. Okay, but first of all, if you noticed in the previous video, part 1 on oxidation numbers, where we were talking about just what are oxidation numbers and how do we use oxidation numbers to analyze redox reactions, I was mentioning the word electronegativity. So we talk about electronegativity in detail in chapter 9, which is the first chapter on chemical bonding. Electronegativity is the measure of an atom's ability to attract a shared pair of electrons in a chemical bond. And so if you think about it, electronegativity is directly applicable, directly related to oxidation numbers, right? In fact, for all of the rules we're about to go through, electronegativity is the basis for those rules. So here's an electronegativity chart. The electronegativities of each of the elements are shown, as you can see. Okay, this chart here is different from the one in the textbook in chapter 9 because I wanted to get electronegativity values with a little more precision. So these go to 2 decimal places as opposed to the one in chapter 9 go to 1 decimal place. And this additional precision is just going to be useful for the purposes of this lecture. Okay, so yes, electronegativity is the basis for the rules we're about to go through, but we aren't going to be completely breaking down these rules in this video from the perspective of electronegativity. Going into all of the electronegativity formulas, etc., that's more of an advanced concept on oxidation numbers, because you can think about how it can get a bit complicated when you've got multiple atoms involved in a compound, but then furthermore, as we've seen, you can have different numbers of electrons being shared, right? We saw with SO2 there was a +4 on the sulfur, and we're about to talk about in a second how most elements have multiple possible oxidation states, both positive and negative. So it's not as simple as just comparing which element is more electronegative than which in a bond to determine the entire nature of the shared electrons and the polarity. Okay, but we actually are going to see in a few minutes that for the specific cases of bonds involving hydrogen, it actually is this simple. So we are going to be able to take advantage of electronegativities to determine oxidation numbers in bonds involving hydrogen without having to go into the full advanced details of calculations of oxidation numbers involving the full electronegativity formulas. Okay, so let's go through these rules. All right, so there's certain rules that I like to call cardinal rules. Certain rules for assigning oxidation numbers that I call cardinal rules. And a cardinal rule is a rule that can never be broken when determining oxidation numbers under any circumstance. And the cardinal rules are very important because what we do is we lean on these rules as much as possible to constrain all of the oxidation numbers of the entire system. You're really going to lean heavily when you're given a chemical compound and you want to assign all the oxidation numbers. You're going to start by leaning as heavily as you can on all of the cardinal rules. And then once you've constrained the system as much as possible with the cardinal rules, then from there you can determine the oxidation numbers that in general aren't as restricted, but based on the cardinal rules that are already present in the compound. Okay, so the first cardinal rule, and this is really the primary cardinal rule that's always used for any compound. Okay, this rule was partially stated in the previous video in this sentence, and that the oxidation numbers for these molecules that we analyzed, they all sum to 0. If you summed the oxidation number on the H and the Cl, it summed to 0, and on the S and the 2 oxygens, it summed to 0. And the reason it says is because the molecules are neutral, so the charges must cancel. Okay, now, but in general, we can come here to rule number 6. So it says, In a neutral molecule, the sum of the oxidation numbers of all the atoms must be 0. In a polyatomic ion, the sum of oxidation numbers of all the elements in the ion must be equal to the net charge of the ion. So yeah, this is just saying that the sum of the oxidation numbers on all of the atoms in a molecule or compound must, under all circumstances, no exceptions, equal the net charge on the entire molecule or compound. Okay, this is the most important, most primary of the cardinal rules of oxidation numbers. This can never be violated under any circumstance. Okay, for example, NH4 plus, they're saying that in NH4 plus, the oxidation number of the nitrogen is -3 and of the 4 hydrogens is +1. So for that to be true, it must be the case that if we take -3 and add to that 4 times +1, we have to get +1. So -3 plus 4 is equal to what? +1. So, okay, the sum rule is not violated here. Perfect. Okay, but note that just because the sum rule checks out, it doesn't mean that those oxidation numbers that the sum rule checked out for are the correct oxidation numbers. You could have multiple different sets of oxidation numbers all check out with the sum rule, right? I mean, so NH4 plus, we could say that the oxidation numbers on the hydrogens is +2, and the oxidation number on the nitrogen is -7. So -7 plus 4 times +2 is +1. So these oxidation numbers obey the sum rule, right? Okay, so it's really just that for any given set of oxidation numbers to be a valid set of oxidation numbers, that set must obey the sum rule. Okay, so here's another example. Cr2 O7 2-. So let's say we know that the oxidation number on each of the oxygens is -2. Okay, but now chromium, like many of the elements in the periodic table, can have multiple different potential oxidation states depending on the compound it's in. Okay, but we can see here that if we know the oxidation number on the oxygens is -2, then the sum rule is going to constrain what the oxidation number on the 2 chromium atoms must be. Because if we say that for each of the chromium atoms, the oxidation number is X, then if we apply the sum rule, we've got that 2 times X plus 7 times -2 must equal -2. So 2x minus 14 is equal to -2. 2x is equal to 12. X is equal to +6. You see? Okay, and so we can come to rule 1 and the first part of rule 2. The sum rule is going to help us to understand these rules. So rule 1 says that in free elements, that is in the uncombined state, each atom has an oxidation number of 0. Thus, each atom in H2, elemental hydrogen, elemental bromine, sodium, beryllium, potassium, oxygen, all of these elemental forms, all of the atoms have the same oxidation number, 0. Okay, so this rule is talking about oxidation numbers on neutral elemental forms of substances. So the entire compound or molecule is made up of the same element. And also that entire compound or molecule is neutral. And it's saying that for these compounds, the oxidation number on each atom will always be 0. And there's no exceptions here. This is a cardinal rule. But where this really comes from is that it's just a result of the sum rule. Okay, because in the previous video, we talked about how any kind of polarity or skew of electrons in a compound can only come about as a result of the presence of different nucleuses and electron clouds that have different numbers of protons and electrons, right? That's the only way you could possibly have any skewing of electrons, any polarity in a chemical bond. Okay, so therefore, for any elemental form of a substance, meaning it's elemental because there's only one type of element involved in the entire substance, there can be no permanent polar type of skewing of electrons, right? You can't possibly have, with a bonding of two H atoms or two bromine atoms, there's no different nucleuses with different numbers of protons or different sized electron clouds to pull electrons from one atom relative to the other. Okay, and so as a result, what you can think about is the main consequence of this is that the oxidation numbers on all of the atoms in any elemental form of a substance must be the same. There's no way that you could have a molecule like this, but then have different oxidation numbers here. Okay, and so as a result, if we've got something like Br2, we see that the oxidation number on each of the bromine atoms is X, and now we apply the sum rule. You have X plus X must equal 0, because that's the net charge on this entire molecule. So 2X must equal 0. That means X is going to have to be equal to 0. Okay, or P4. If we say that the oxidation numbers on each of the phosphoruses is X, then applying the sum rule, you've got X plus X plus X plus X, 4X must equal 0, so X must be 0, right? So you can see how if for any elemental form of a substance, a neutral elemental form, that's why the oxidation numbers on each of the atoms is going to have to be 0. Okay, but we can extend this to elemental forms of ions as well. So the first part of Rule 2 talks about the oxidation numbers on monoatomic ions. It says, for ions composed of only one atom, that is monoatomic ions, the oxidation number is equal to the charge on the ion. Thus, the Li plus ion has an oxidation number of +1, Ba2 plus ion +2, etc. So for any monoatomic ion, the oxidation number on that single atom is just the charge, whatever the charge of the ion is. But we talked about this in the previous video and how this makes intuitive sense from our understanding of the meaning, the definition of oxidation numbers, right? The hypothetical ion that's created, in this case, isn't hypothetical, right? With oxidation numbers, you have these polar, most of the time it's these polar molecules, these polar compounds, but then you assume a hypothetical full transfer of the electrons associated with that polarity, and then whatever hypothetical ions result, whatever those charges are, is the oxidation numbers. Well, for the case of an actual literal ion, there you don't have to do any hypothetical transfer of electrons. Like it's all about just tracking the electrons, right? That's the whole purpose of oxidation numbers. Well, with ions, it's easy because you actually do know where exactly the electrons are. So you just put the oxidation number for an ion is just the charge of the ion, at least for a monoatomic ion, where you're only dealing with one atom, right? Like this also makes sense from the perspective of the sum rule. So Fe3 plus, well, okay, if the oxidation number on the single iron atom is X, you apply the sum rule. Well, X needs to equal the total net charge here, which is +3. Okay, but as we know, there's also elemental forms of ions that aren't monoatomic, but diatomic or polyatomic, like O2 2-, for example. Okay, so once again, this is an elemental form, so even though this is an ion, there still can be no skewing of electrons between these two oxygens, right? They're going to have the same oxidation number, which we'll say is X. So now if we apply the sum rule restriction, then 2 times X, which is X plus X, has to equal, under all circumstances, the net charge, -2. So X has to be -1. Okay, but now we can also come to Rule 7 here. It says oxidation numbers do not have to be integers. And it gives the example of the superoxide ion, O2-. Okay, you can think about how this ion has been observed to exist in some circumstance. Okay, and so this does exist. We know this can be formed. So, okay, we need to assign oxidation numbers here. Well, okay, there's no way the two oxygens can have different oxidation numbers because it's like an elemental form, right? You have all the same nucleus and the same electron clouds. Okay, but now from here, the sum rule is going to dictate what this X has to be. Because again, the sum rule is a cardinal rule. It cannot be violated under any circumstance. For any compound you're analyzing involving oxidation numbers, the sum rule can never be violated, no matter what. So, okay, that means that 2x must equal -1. And so this shows you that we have to, since the sum rule can't be violated, we have to allow for non-integer oxidation numbers. Here's an example. Okay, so everything we just talked about was constrained by the sum rule. Okay, so what's another cardinal rule? Well, if we come to the second part of Rule 2, here's two cardinal rules here. So all alkali metals have an oxidation number of +1, and all alkaline earth metals have an oxidation number of +2 in their compounds. Okay, so again, these are cardinal rules. They cannot be violated under any circumstance when it comes to assigning oxidation numbers. So let's say you're presented with the compound sodium bicarbonate, NaHCO3. Okay, well, the first thing you're going to look for is, are there any alkali metals or alkaline earth metals? So we see here we have a sodium as an alkali metal. So we immediately just come straight to the sodium and put a +1 here. Okay, another example, let's say we're presented with the compound magnesium sulfate, MgSO4. Okay, well, first thing we're going to do is look and see, are there any alkali metals or alkaline earth metals? And magnesium is an alkaline earth metal. So we come straight to the magnesium and put a +2. So, okay, now another cardinal rule is this first sentence of rule number 5. So fluorine has an oxidation number of -1 in all of its compounds. That's another cardinal rule. So, okay, so once again, for example, if you're presented with a compound like trifluoromethane, CHF3, well, we start by looking for if there's or any alkali metals, alkaline earth metals, or now fluorine atoms. And here we see there are 3 fluorine atoms. So we immediately go ahead and assign a -1 oxidation number to each of the fluorines. Okay, now a quick note. These last 3 cardinal rules we just went over with the alkali metals, alkaline earth metals, and the fluorine, these rules are referring to when these elements are contained within compounds, not elemental forms. So remember, a compound contains more than one type of element. That's the technical definition of what a compound is. If it only contains one type of element, we call that an elemental form. But so in an elemental form of fluorine, so F2, for example, well, okay, in this case, we wouldn't come here and apply this rule 5 and put a -1 on each of the fluorines, right? That would violate the sum rule. -1 is -2, not 0. No, this is going to go by the whole logic of you can't have any skewing of electrons here. It's the same atom, or it's atoms of the same element, so these oxidation numbers are going to have to be 0. Okay, so the rules we just went over were referring to any circumstance where you have an alkali metal, an alkaline earth metal, or a fluorine atom is in a compound, which means it's bonded to some other type of element. And therefore, there's polarity at play, differences in electronegativities. Then in those cases, in all circumstances, no exceptions, an alkali metal is going to have an oxidation number of +1, alkaline earth metal +2, and then fluorine -1. Okay, and based on our understanding of the definition of oxidation number, we understand what this means. It means that there's no circumstance where an alkali metal is bonded to some other type of element in which that lone outer valence electron on the alkali metal isn't pulled away from the alkali metal nucleus to some degree. Same idea with a fluorine. There's no circumstance where a fluorine is bonded to some other type of element in a compound in which the fluorine isn't pulling a single electron towards it to some degree to complete that outer shell and achieve the noble gas configuration. Okay, but now we also see rules written here at the end of rule number 2. So it says aluminum has an oxidation number of +3 in all of its compounds. Okay, so is this a cardinal rule as well? Well, technically, no. So if we come to the next page, the textbook gives this chart, and this chart shows common possible oxidation numbers of different elements. Okay, so you can see the alkali metals just show a +1, alkaline earth metals just show a +2, fluorine just shows a -1. And that's the only oxidation numbers that are listed for these elements, right? Has to be. But for other elements, you can see there's multiple possible oxidation states, depending, and these states just depend on the compound that element is in. Okay, in red, if an oxidation state is shown in red, that's the most common oxidation state for that element, and in black is still a common oxidation state, but less common than the one shown in red. Okay, and so the rules the textbook gives, all of these rules, and there's a few more rules here, are based on this chart. So we can see aluminum, all that's shown is +3, right? Okay, however, while this chart does show the most common oxidation states that you'll see in general for these elements, the majority of the time, it's not 100% foolproof. There are exceptions to what's shown in this chart. So, for example, the compound aluminum monofluoride. This compound has been seen to exist, but it's an unstable, high-temperature gas phase molecule that quickly reverts back to the reactants it was formed from, but it has been observed to exist. Okay, so we can think about, all right, this is a compound that can, in some circumstances, be formed. So, okay, let's assign the oxidation numbers here. Well, the first thing we want to do is look for any way we can constrain this with cardinal rules. Are there any alkali metals, alkaline earth metals, fluorine atoms? And there is a fluorine. And under no circumstance whatsoever can a fluorine, if it's in a compound, so it's bonded to other elements other than fluorine, the fluorine atom can never not have an oxidation number of -1. So we put a -1 here. Okay. Now, also under no circumstance can the set of oxidation numbers of a molecular compound violate the sum rule. Okay. Now, since we only have one element remaining here, just this aluminum atom, well, the sum rule is going to dictate what this oxidation number on the aluminum has to be. So if this is X, then X plus or X minus 1 has to be equal to 0. So X has to be +1. And there you go. There's an oxidation number for aluminum that's not +3. Okay, but however, in general, it's very uncommon to see a compound that contains an aluminum in which the aluminum has an oxidation state other than +3. The +3 rule for aluminum is not a cardinal rule, but it's very close to being a cardinal rule. And same with, so if you ever have a halide in a compound, so that's a halogen with a negative oxidation number, and we're not talking about fluorine here. Fluorine's already fully constrained. So any one of the halogens other than fluorine, that's a halide, meaning it's in a negative oxidation state. So in the name of the compound, you would call it an ide, right? If you think about from chapter 2, when we talked about naming compounds, the naming convention for ionic compounds, you just use that same convention for molecular compounds as well. That's like the general idea. So we call, like, we have sodium chloride in NaCl. That's an ionic compound. But if you had some molecular compound involving chlorine where the chlorine was in a negative oxidation state, you would call it a chloride as well. So if you ever have a compound in which you're dealing with a halide other than fluorine, so like a chloride, bromide, iodide, it's very, very uncommon to ever see a halide with a negative oxidation number other than -1. So yeah, there's a bunch of different potential positive oxidation states, but if the oxidation state is negative, if it's a halide, it's very uncommon to see a negative oxidation number on a halide other than fluorine that's not -1. Yeah, fluorine will always be -1. This only occurs in highly unusual compounds, where you can think about it, it would typically be like these compounds are very unstable. They don't stay connected long. They do form, but they don't stay formed for long. And this is taking place under non-standard pressures and temperatures. For example, Li3Cl, lithium chloride. These compounds have been observed to exist, even if very briefly, in a highly unstable, non-standard temperature and pressure state. Okay, but they have been observed to exist, so we can think about what are the oxidation numbers on the atoms in this compound. Well, okay, we see we have 3 lithiums here. Lithium is an alkali metal, so each of the lithiums is going to have an oxidation number of +1. And now for the chlorine atom, the sum rule is going to constrain the oxidation number on the chlorine atom. So if this is X, then the sum rule states that 3 plus X has to be equal to 0, because Li3Cl is neutral, right? So X is going to have to be equal to -3. And there you go. There's a negative oxidation number on a halogen that's not -1. Okay, and so again, the aluminum +3 and the halogens having, other than fluorine, having a negative oxidation number other than -1 are very rare, but these are not cardinal rules. Okay, but and then again, in general, even having an oxidation state on one of these elements that's just not shown in this chart is rare as well. Okay, so now the next cardinal rule relates to hydrogen, the oxidation states of hydrogen. Hydrogen is going to have an oxidation state of +1 or -1. One of those two. Nothing else is possible. This is a cardinal rule. Okay, now when I was first learning oxidation numbers, this rule wasn't as useful as I initially realized. For example, let's look at the compound sodium borohydride. Okay, we see an alkali metal here, so we put +1. Okay, now boron in the chart is shown to have a single most common oxidation state of +3, but it is possible for boron to have oxidation states other than +3, right? We aren't going to be making any statement in this video about a cardinal rule involving boron saying that boron can only have an oxidation state of +3. So in general, we can't just come straight to the boron here like we did with the sodium and put +3. No. Even though from a probability standpoint, it is very likely that the boron oxidation state in this compound is going to be +3, we can't state that officially with 100% assurance. Okay, and so since hydrogen can have multiple possible oxidation states as well, when I was first learning oxidation numbers, if I was trying to apply the oxidation numbers to this compound, I would be stuck here. Because you can't use the sum rule at this point, because you'll have one equation with two unknowns. If we say that each of the hydrogens has oxidation number of X, the boron Y, then applying the sum rule, you've got X plus Y plus 1 equals 0. That's two unknowns in one equation. Okay, but what I didn't realize is that the hydrogen cardinal rule is more useful than it seems. Because while it's not as restrictive as like the alkali metal, alkaline earth metal, and the fluorine rules, it is still very restrictive, right? Because there's only two possibilities. So we could think about making two columns, for example. One column corresponds to the oxidation state of +1 for the hydrogen, and the other -1. And then what we do is we work out the oxidation state of on the boron for what the boron must be in each of these circumstances. So in this case, for +1 on the hydrogen, you've got +4 +1. So to make 0, you'll need -5. For a -1 on the hydrogens, you've got -4 +1 is -3. Then you'll need a +3 for the boron here, right? And so you can see now we have a clear picture. The boron oxidation state for this compound is going to have to be -5 or +3. It has to be one of those two. No exceptions. Why? Well, because otherwise the oxidation state on the hydrogens would be something other than + or -1, which that can't happen, right? That's a cardinal rule that can't be violated. And so you can think about maybe when you go through an analysis like this, maybe one of the outcomes isn't possible. And so you could cross it off, and that leaves you with only one other possibility. Like, for example, if we come here to these three rules, so the first rule, it says metallic elements have only positive oxidation numbers, whereas non-metallic elements may have either positive or negative oxidation numbers. And, well, this actually isn't a cardinal rule. So if we come to the table, so yes, you don't see any metals with any listed negative oxidation numbers. So it is very rare in general to ever find a metal within a compound that has a negative oxidation number, but it's not impossible. It's not impossible. That's not a cardinal rule for metals. For example, cesium auride. Cesium bonded with gold. So this compound has been observed to exist under certain circumstances in certain conditions. All right, so we see a cesium here, which is an alkali metal, so we put a +1. And then the sum rule dictates that the oxidation number on the gold must be -1. Okay, and there you go. There's a negative oxidation number on a metal, on gold. Okay, but now this second rule here, this is a cardinal rule. This can never be violated. So it says the highest oxidation number an element in groups 1A to 7A can have is its group number. For example, the halogens are in group 7A, so their highest possible oxidation number is +7. Okay, by highest, they're not referring to highest in magnitude. For example, like +2, we would say is higher in this case than -3. And so what this rule is saying is that for any elements in groups 1A to 7A, so not including these middle columns here or the noble gas column, just these first two columns and then these 5 columns here, it's not possible for these elements to ever have an oxidation number higher than their group numbers. So nitrogen or phosphorus, for example, could never have an oxidation number of like +6 or +7. Or like carbon, silicon, or tin could never have an oxidation number higher than +4. So it couldn't have an oxidation number of like +5 or +6, for example. Okay, and so now then coming back to this sodium borohydride example here, maybe one of these outcomes results in an oxidation number that violates this group number rule, right? In which case you cross out that option and you'd be left with the other option would be the only option for the oxidation number on the hydrogen. Okay, but even if some rule isn't violated, like in this case, -5 is a possible oxidation number for boron, and then obviously so is +3, this still gives you a clear picture on what you're dealing with, right? The hydrogen cardinal rule is still very useful. Okay, but still though, if we're trying to label the oxidation numbers here, both of these are possibilities. So what do we do? Okay, if we come to rule number 4 states that the oxidation number of hydrogen is +1, except when it is bonded to metals in binary compounds. In these cases, like for example LiH and AHCAH2, its oxidation number is -1. Okay, but sodium borohydride doesn't quite fall under this category, right? This is a ternary compound, and here they're talking about binary compounds. Okay, but here's a trick we can use for hydrogen. And this is a cardinal rule we can apply to hydrogen. So because hydrogen is a simple case of only two possible oxidation states, one being a positive oxidation state and one being negative, we can use electronegativities in a simple way for the case of hydrogen. So for any chemical compound involving hydrogen, what we can do is we can look at the structure of that compound. So here's the structure of sodium borohydride. And we can see this is actually an ionic compound, a bond between Na plus cations and BH4 minus anions. But okay, we want to look at the structure because we want to see what the hydrogens are directly bonded to. In this case, they're bonded to boron. And so now all we need to do is compare the electronegativities of the hydrogens to whatever element they're bonded to, and in this case, boron. So we can see here that hydrogen has a higher electronegativity than boron. Therefore, we can state that the oxidation state on the hydrogen is going to be negative, -1, which means that the boron oxidation state is going to be +3. Okay, and so that's the main cardinal rule that you want to use involving hydrogen. You just compare the electronegativities of hydrogen and whatever element the hydrogen is bonded to, whichever is larger will dictate the oxidation state on the hydrogen, whether or not it's the positive +1 or negative -1 oxidation state. Okay, and so that's where rule number 4 is coming from. However, when we get around the metalloids, this rule can get a little confusing. For example, so phosphorus is a nonmetal. Therefore, we would expect hydrogen to take on the positive oxidation state when bonded to phosphorus, right? But look, hydrogen has a slightly higher electronegativity than phosphorus. Okay, and then looking at a lot of these metalloids, we would potentially expect hydrogen to take on a negative oxidation state when bonded to a metalloid. So boron, silicon, germanium, arsenic, antimony, tellurium, all of these have lower electronegativities than hydrogen, except for astatine. Astatine is considered a metalloid. Astatine has the same electronegativity as hydrogen, but still the majority of the metalloids, all but one, are listed as having a lower electronegativity than hydrogen. Okay, but what you can think about is that once you get to electronegativities that of an element that is very close to the electronegativity of hydrogen, in this case, for example, that would be like arsenic, astatine, or even tellurium's pretty close. Okay, in these cases, it can get a little more complicated because, for example, there's different scales for measuring and calculating electronegativity. The Pauling scale, the Mulliken scale, Sanderson, Allen, etc. Okay, but one thing to remember is that oxidation numbers aren't so much about describing a physical reality as they are just a tracking device for electrons in chemical reactions, right? So that's why you could potentially make a rule that says something like, we're just going to say if you have a hydrogen bonded to a phosphorus in a chemical compound, well, since phosphorus is a nonmetal, then we'll just make the rule that when hydrogen is bonded to phosphorus, the hydrogen takes on the positive oxidation state, right? You could make a rule like that, and that's the general rule that everyone follows in the scientific community for assigning an oxidation number to hydrogen when it's bonded to a phosphorus. Okay, but like boron, silicon, germanium, antimony, these are different enough from the electronegativity of hydrogen to where you can just say that hydrogen is in general, more electronegative than these elements. It's only with arsenic and astatine, maybe tellurium, and even phosphorus, where it's close enough to where you can consider hydrogen bonded with these elements as more advanced concepts in oxidation numbers that you would need to look into more deeply on your own. This would be beyond the scope of this video, this course. Okay, but now this brings up another question. Is it possible for the same element in a compound to have different oxidation numbers? Like, for example, we haven't really talked about why I've just been automatically assigning, like, -1 to all 4 of these hydrogens, assuming they're all going to have the same oxidation number, all of the hydrogens. Okay, well, for sodium borohydride, these hydrogens are going to all have the same oxidation number. It doesn't make physical sense that these hydrogens could have different oxidation numbers. Yes, mathematically, they could have different oxidation numbers and still satisfy the sum rule, right? As long as the sum of the oxidation numbers on these 4 hydrogens adds to -4, then the sum rule isn't violated. But how could these possibly have different oxidation numbers? Okay, like to add to -4, how could this be -6, and then this be +4, and then this be -1, and this be -1, right? Because you have the same boron nucleus and electron cloud interacting with the same hydrogen nucleuses and electron clouds. Okay, but atoms of the same element can have different oxidation numbers in a compound. This can happen if those atoms are bonded to different types of elements. For example, the compound acetic acid, C2H4O2, also known as we can write this as CH3COOH. Okay, and it's written this way because of the structure of this compound. Right, and so we can see that in the compound there's hydrogens in different locations, and specifically bonded directly to different elements. Here, this hydrogen is bonded to an oxygen, and here these hydrogens are bonded to a carbon. So to determine the oxidation state of the hydrogens, we compare the electronegativities of hydrogen to carbon and oxygen. Okay, so in this case, both carbon and oxygen have higher electronegativities than hydrogen. So it turns out that all 4 hydrogens in this case, in this compound, are going to have the same oxidation number of +1. But you can think about how in another circumstance, maybe a lone hydrogen like this, or some separate hydrogens in a compound, would be bonded to an element with a lower electronegativity. Okay, but even with acetic acid, the 2 carbons are going to have different oxidation numbers. In CH3, the oxidation state of the carbon is going to be +3, and in COOH, the oxidation state of the carbon is going to be -3. Okay, so how does this happen? And how would we know to assign these electronegativities to the carbons? Well, again, as I mentioned at the start of this video, to assign oxidation numbers, you are going to really want to lean heavily on the cardinal rules. So the cardinal rules for hydrogen dictate that you have a +1 assigned to all of the hydrogens. Okay, and now we can come to the next cardinal rule that involves oxygen. And this is like what I would call a sub-cardinal rule, sort of like a little brother of the main cardinal rules we've listed thus far. I say that because the rule for oxygen is that oxygen will always have an oxidation number of -2 unless one of the cardinal rules we've talked about thus far forces oxygen to have a different oxidation number. Okay, so it says here in Rule 3, the oxidation number of oxygen in most compounds, for example, magnesium oxide and H2O, is -2, but in hydrogen peroxide, H2O2, and peroxide ion, it is -1. But we also saw with Rule 7 that you had oxygens with oxidation numbers of -1/2, we can see in the table of oxidation numbers, there's 4 oxidation states listed, with -2 being the primary one in red. Okay, but this rule can be summarized in general with, again, the statement that oxygen is always going to have an oxidation number of -2, no matter what, unless one of the cardinal rules we've talked about so far, so the sum rule, the rule for hydrogen, the rule for alkali metals, alkaline earth metals, the rule for fluorine, but like not the oxidation number of +3. That wasn't a cardinal rule, right? Only the cardinal rules we've discussed. If one of those rules forces oxygen to have an oxidation number other than -2, then that happens. Otherwise, the oxidation number on oxygen in a compound is going to be -2, right? So again, you had the O2 to minus, right? Well, okay, the sum rule cannot be violated under any circumstance. And so if the oxidation number on each of the oxygens is X, then X plus X, 2X, must equal -2. So it forces the oxidation number on oxygen here to be -1. And same idea here with O2 minus. The sum rule forces the oxidation number on the oxygens to be -1/2. And then another example they give here is with H2O2. Okay, well, hydrogen is, in this case, the two hydrogens are bonded to the more electronegative oxygens. So the oxidation number on the hydrogens is going to be +1. Now from here, the sum rule is going to dictate what the oxidation numbers on the oxygens must be. So 2 times +1 plus 2x has to equal 0. 2x is equal to -2. So x has to be -1, you see? Okay, but after these main cardinal rules, again, the sum rule, the alkali metals, alkaline earth metals, fluorine, after these main cardinal rules, then the oxidation number of -2 on oxygen is going to take precedence and will dictate oxidation numbers of other compounds. And so coming back to acetic acid here, we can see that the oxidation numbers on the two oxygens is, there's no cardinal rules that are dictating the oxidation numbers on the oxygens, so we're going to put -2. And now you might say, well, what about the hydrogens here? Isn't the cardinal rule involving hydrogens at play, right? Like, why did I just say that the hydrogens aren't going to affect the oxidation number on the oxygens and just put -2? How do I know that the hydrogens aren't forcing the issue with the oxidation number on these oxygens? Well, no, because we have another element here. We have carbons that can allow the oxygens to obey its -2 oxidation number cardinal rule without messing with the hydrogen cardinal rule. It was only the case with the H2O2, the hydrogen peroxide, for example, that oxygen had to take on an oxidation number other than -2 because there was no other option. Here, there is another option, right? The oxidation numbers on the carbons can allow the oxygen to obey its -2 oxidation state cardinal rule at the same time as the +1 oxidation state on these hydrogens. And since we're saying that this rule for oxygen is a cardinal rule, it takes precedence, then again, it's going to dictate what the oxidation numbers on all the other elements are. So if there's any way whatsoever that we can have oxidation numbers on these two carbons, even if they're different, and then at the same time you've got the rule for hydrogen obeyed, and the -2 for oxygen obeyed, and the sum rule, then that's going to be the oxidation state. Okay, and so now we can see that with the oxidation numbers on the hydrogens and oxygens assigned, summing all of these numbers, you have +1 + 1 + 1 + 1 is +4, -2 is 0. So since this entire molecule has a 0 charge, that means the sum of the oxidation numbers on the carbons is going to have to be 0. So how do we figure out what the oxidation numbers must be on the two carbons? Well, okay, for the CH3 carbon, we know that at least 3 electrons are in its vicinity. coming from the 3 hydrogens, right? That's what this +1 oxidation state is going to mean. Okay, now next we look at this last bond that this carbon has with the other carbon in the COOH group. Okay, so now another cardinal rule that we can use specifically if we're analyzing a compound from a structural standpoint like this is that if we're looking at individual bonds between 2 atoms and trying to get a sense for how electrons are skewed in those bonds, so like we just did here with the carbon-hydrogen bonds, okay, if you're looking at a bond between the same element, right, this bond here between 2 carbons, between the same element, then you can assume that there's no skewing of electrons within that bond. Okay, and so now with that then, because we're assuming there's no skewing of electrons here, so that there's no electron coming into the vicinity of this carbon from this carbon, or vice versa, one leaving this carbon and being skewed towards this carbon, and then we know that these oxidation numbers on these hydrogens are +1, so there's 1 electron being skewed away from each hydrogen towards the carbon. Well, that means that the oxidation number on this carbon must be -3. And now, for the sum rule to be obeyed, that means the oxidation number on this carbon is going to have to be +3. And there we go. There's the oxidation numbers on acetic acid. All right, you would put, let's see, -3, +1, +3, like that. Okay, now, you might look at this and say, well, wait, for the COOH group carbon, if we've got the 2 oxygen atoms pulling 2 electrons each away from the carbon, and then there's no skewing of electrons here, well, then shouldn't the oxidation number on this carbon be +4? Yes, ideally that's true. But once again, the hydrogen is going to take precedence. And we can think about why the hydrogen cardinal rule takes precedence in that. So, okay, we know hydrogen only has 1 electron in its electron cloud, right? However, oxygen has 8 electrons, 6 of which are outer valence electrons. So with oxygen having 6 valence electrons, that leaves room to say that potentially there's on average, about 3 electrons pulled away from the vicinity of this carbon atom by these 2 oxygens, right? That could potentially, in reality, be the case. But when you're dealing with hydrogens, there is no wiggle room like this because there's only the 1 single electron associated with any given hydrogen atom. That's why it would make no sense to apply any kind of oxidation number that would suggest that there's more than 1 electron being pulled away from a hydrogen or even towards a hydrogen. You might say, well, okay, well, why couldn't a hydrogen potentially pull like 2 electrons towards its vicinity to where it would have an oxidation number of -2? Yeah, an oxidation number greater than +1 doesn't make sense because how could you pull more than 1 electron away from a hydrogen, right? But what about maybe a hydrogen could pull like 2 electrons towards it, let's say, and have an oxidation number of -2? Well, no, because a hydrogen only has 1 proton in its nucleus. It doesn't have the power to pull more than 1 electron towards it. Okay, and so again, that's why the oxidation numbers of hydrogen only being able to be plus or -1 has to take precedence. That has to be a cardinal rule that's never violated when doing oxidation numbers. Okay, and so with this at -3, then no oxidation number other than +3 that we can assign to this COOH carbon. Otherwise, the sum rule would be violated. And so there we go. That means this has to be +3. Okay, but again, also just remind yourself of the purpose of these oxidation numbers and that it is just a tracking device for electrons. So it's not the end of the world if an oxidation number assigned to an atom is not this like absolute perfect reflection of reality, as long as it's close enough to paint a picture of the general positioning of electrons in a compound. Okay, another example of atoms of the same element in a compound having different oxidation numbers is ammonium nitrate. So NH4NO3. Okay, in ammonium nitrate, the two nitrogens have different oxidation numbers. Okay, and well, you can see here that ammonium nitrate is an ionic compound, and so with ionic compounds, it's like you have two distinct molecules or compounds in a sense, right? With the two ions. So when you're dealing with an ionic compound, you can sort of assign oxidation numbers to each of these ions independently, in a sense, right? And so you can see how it makes sense how the nitrogens here could end up having two separate oxidation numbers. Okay, so these hydrogens are bonded to the more electronegative nitrogen, so they're going to have oxidation number of +1. For these oxygens, there's no cardinal rule overriding anything, so the oxidation numbers on the oxygens are going to be -2. Okay, now we can just apply the sum rule individually to each of these ions. So you have +4, and you need to end up with a +1. So the nitrogen oxidation number on NH3 or NH4 plus is going to have to be -3. Here we need to end up with a -1. We have -6, so the oxidation number on the nitrogen here is going to need to be -5. And there we go. So we put, or no, +5. Okay, and so that's it. There's an overview of how to assign oxidation numbers to the atoms of a given compound. But assigning oxidation numbers is one of those skills that takes practice. So we're going to work a bunch of practice problems in the next video or 2 videos.